Hello everyone, and welcome to session 1 of the Shimadzu LC Purification series. This series of webinars is designed to introduce and increase your knowledge in this area. The first session in this series is looking at the fundamentals of LC purification. My name is Richard Hodson and I'll be your presenter today. I am part of the LC technical team at Shimadzu in the UK. The Shimadzu LC Purification webinar series will consist of 3 sessions. The first today is titled Fundamentals of LC Purification. This will include what is LC purification, how much sample can you expect to purify, upscaling basics, and recycling and concentration. Session 2, titled Semi-Micro to Analytical Scale LC Purification, will cover the differences between semi-micro and analytical scale prep, principles, things to consider, instrumentation, and software advantages. Lastly, session 3, titled Semi-Preparative and Other LC Purification Techniques. This will cover principles, common issues, and tips and tricks of semi-preparative chromatography, UFPLC, ultra-fast preparative and purification LC, and semi-preparative SFC scale purification. What is liquid chromatography LC purification? First, let's think about analytical LC. Shown is a chromatogram for the separation of 16 cannabinoids, and in analytical LC we are interested in qualitative information, that is, which analytes corresponds to which peaks, and quantitative information, that is, the concentration of each analyte in the sample. We can use non-destructive detectors such as UV and PDA, or destructive detectors such as mass spec or ELSD. The eluent typically flows to waste, and we are no longer interested in the actual sample, just the data that we acquired from it. However, when considering LC purification, we are interested in physically separating and isolating, or purifying, an amount of one or a number of components in a sample. Like analytical LC, we can use any detector we require. But if using a destructive detector, we require a split of the eluent, a small proportion going to the detector, while most go into the collection. In this example, we are interested in isolating and collecting the blue analyte, whereas the red isn't required and can go to waste. We need to consider the demands placed on LC purification according to our final goal. These demands include purity of our isolated analytes, yield, or the quantity of isolated analytes, and also the rate or throughput, basically how quickly we can achieve the yield of isolated analytes of the desired purity. However, it is impossible to maximize all of these demands at once. If we achieve an average purity and an average yield and an average rate, then we are somewhere in the middle. Increasing both yield and purity requires a compromise of the rate. Maximizing purity requires a compromise to both rate and yield. The purity, yield, and rate demands are a common theme which run through this presentation. Before we start with any preparative LC, we should have a good idea of the yield and purity we require. The rate can be dependent on the capability of the hardware and the column dimensions which are available to you. Who is interested in LC purification? Academia, pharma and life sciences, food and beverage industry, and also the chemical industry. Why? They may be interested in the purification of synthetic products and impurities. They may want structural or biochemical analysis being done, or they may require enough high purity material for the next synthetic step. They also might be interested in isolating active compounds in natural products. Possibly sample pre-treatment. Some analytical methods require a sample isolated from a matrix using LC purification. Or they may be interested in commercial production. What changes in each of these situations is the amount, the yield, the required purity, and the equipment available, which affects the rate. If we look at this chart, we can see the general descriptions for different LC column sizes. Down at low flow rates, we have narrow 2 mm ID columns, sometimes referred to as semi-microscale. Then around 4.6 mm ID columns at analytical scale, 20 mm ID columns at semi-preparative scale, and lastly 50mm ID columns of flow rates of up to 150 millilitres per minute of preparative scale. We can go larger than 50mm ID, but these are typically referred to as industrial scale and can have flow rates of several litres per minute. Each of these column sizes has a typical to maximum loading, but as you can see, this range tends to be large and is really only a guide. Different industries and departments are interested in different scales. For example, biochemical materials may only be needed in very low amounts and therefore can be purified on a narrow ID column. In sessions 2 and 3 of this series, my colleague Earl McCoy will go into more detail about these scales. LC Purification Workflow. Step 1. Purity, yield, and what equipment is available to us should be known. Step 2. Optimization of the separation conditions and assessment of loading in analytical scale, typically on a 4.6mm ID column, but not essential. What is essential is using a column with the same phase as any larger semi-prep or preparative column you have available. Step 3. Use this information to scale to semi-preparative or preparative LC. You can calculate the number of injections likely to be required, amount of solvent used, and the time it will take. Not everybody will need to scale up, however. As you'll see in the next session, not everybody needs to use large-scale columns. Step 4. Once you have run all your injections, the collected compounds are typically re-analyzed to confirm purity. Optimization in analytical scale. The most important thing in LC is to achieve the maximum resolution in the minimum amount of time. We can calculate the resolution in a chromatogram between two peaks using each peak's width and retention time. To achieve this resolution, 3 parameters are important: efficiency, selectivity, and retention. In LC purifications, we are concerned with getting the required yield at the required purity in the minimum time. To do this, we typically overload our injections. That is, we try and get as much material onto the column as possible without completely losing all separation between analytes. As peak widths increase dramatically when we overload, the impact efficiency has on resolution is dramatically decreased. Therefore, selectivity is increasingly important. A whole range of column dimensions are available. A few standard internal diameters are listed here, although some sizes are available in between. Maximizing column loading increases yield and increases rate at the acceptable peak purity. When scaling between columns, the loading amount is proportional to the column volume. Let's look at an example. We've been given an analytical method which contains 2 peaks, A and B. We want to isolate and collect peak A, but peak B is not required. We're running a 250 by 4.6mm 5 micron C18 column, and our analytical method injection volume is 5 microliters. We require 700 milligrams at greater than 92% purity. We have an LC instrument that can handle up to 20 mils per minute, and we have a 20mm ID column in the same phase, length and particle size as the column used for the analytical method. The analytical method looks reasonable, good resolution between peaks A and B, and good retention of the first peak. We have high solubility of the sample in our injection solvent, and after making a concentrated solution, we can inject 5 microliters onto the 250 by 4.6 analytical column with a recovery of approximately 1 milligram of peak A. So although the purity is very high, yield and rate is too low. We need to increase the loading. So we can increase the injected volume and therefore mass on column. Peaks are not touching, high purity, 2 milligrams of analyte. Let's inject more. Again, peaks still not touching. High purity, 4 milligrams of analyte. Let's keep going. Here the peaks are touching, but only just. We have lost a little purity. Now if we double the injection volume, we have partial co-elution. We are having to stop collecting the fraction partway down the back slope because we are getting a mixing of the 2 peaks. Our purity has dropped, but it's still higher than the greater than 92% requirement. We have taken the method optimization at analytical scale as far as we can. If we were to carry out our LC purification on this analytical scale column, at this loading, we'd be looking at 34 injections and 17 hours to hit our 700 milligram target. We would have the purity we require and a yield which is good for a small column, but the rate is very poor. We should therefore scale up to a larger ID column, but one of the same length, phase, and particle size. Scaling from a 4.6mm ID column to a 20mm ID column is approximately a 20 times increase in cross-sectional area. Therefore, a 20 times increase in injection volume, flow rate, and amount of material on column should provide the same resolution of peaks. Now with the 2000 microliter injection on the 20mm ID column, we can purify our 700 milligrams in greater than 94% purity in 2 injections or 1 hour. Not an astounding rate, but much better than the original 17 hours on the analytical column. The graph shows the effect of particle size on resolution. The line with blue circles represents a 20mm ID column with 5 micron particles. The other line represents 20, 30 and 50mm ID columns, but with 15 micron particles. At analytical loading, smaller particles gives clearly higher resolution. However, at preparative loading, the effect on resolution of the smaller particle size decreases. Due to the cost, preparative scale LC purification usually employs columns of larger particle size. The elution order of peaks can make a big difference to purity and yield. If an impurity, shown here in red, elutes before a major band, then as overloading occurs, the large amount of material in the major band displaces this smaller peak, pushing it to a lower retention time and importantly prevents significant mixing, therefore keeping high purity. However, if the impurity elutes after a major band, then as overloading occurs, in this case, the small impurity peak is tagged along by the major band, pulling it under and greatly decreasing the purity and therefore probable yield. We are not always lucky enough to be able to make sure our impurity peaks elute before a major band rather than after, but in the case of chiral separations, some chiral phases are available in opposite enantiomers, thereby giving you the option of switching elution order. The diagram shows the effect injection solvent has on the analyte band in the column. If we assume this is a reversed phase method and we inject in water, which is our weak solvent, then the width of the analyte band is maintained. However, if we inject in a strong solvent such as methanol, then the effect of this volume of strong solvent is to carry some of the analyte with it down the column. This spreads our analyte band and is usually referred to as band broadening. This graph shows the effect of injection solvent strength and volume against the number of theoretical plates in a column. Again, let's assume this is a reverse phase method, and you can see that 100% water has little effect on plate number as the volume increases. But 100% methanol, or a 70-30 mix of water methanol, significantly decreases plate numbers as injection volumes increase. We can see the effect of this in real chromatograms. There are 3 shown here. All use 100% methanol as the injection solvent, but the top chromatogram is 100 microliters, the middle 50 microliters, and the bottom 10 microliters. The chromatogram with only 10 microliter injection shows a reasonably tight narrow peak. At 50 microliters, we see significant band broadening, and 100 microliters, we even see some breakthrough, and the start of the peak is seen way down between 2 and 4 minutes retention. For large injection volumes, we require weak solvent, or our purity and yield will be compromised. What is recycling? Let's look back at our previous example of overloading and scale-up. We were using a basic LC setup with a pumping system that allowed up to 20 mils per minute, so we were okay running a 20mm ID column. We decided to stop collection partway down the back slope of peak A due to mixing of the two analyte bands in the region highlighted. Analytes in this region are therefore diverted to waste, but if your sample was in short supply or took a long time to synthesize, then you might not be happy throwing this proportion of peak A away. What we want to do is recycle. This can be done manually by collecting the peak, drying down, reconstitute and re-injecting, all of which takes a long time. A better way to do this is automatically. If we fit a recycle valve after the detector and before the collection, any such mixed bands can be rediverted back into the flow path so it passes through the column a second time, leading to an increase in yield. When we have a system looping back round into the flow path, this is known as closed-loop recycling. With it, we can only use isocratic elution. The recycled band repasses through the pump and autosampler. Therefore, the pump should have minimum internal volume, and the autosampler loop should be bypassed during the second, third, and subsequent elutions. With alternate recycling, we have two identical columns. We still only have isocratic elution, but the sample band alternates between columns by valve. We can use the detectors to control the switching of the valve so that we can keep our analytes in the loop for as many elutions as required before allowing them to leave the loop to be collected. We know that increasing column length increases efficiency and in turn increases resolution. But what happens when we are already using the longest column available? Add a second or further columns? Or we could recycle the whole peak repeatedly to increase resolution. Take this example here, where after one elution we have the two analytes, isopropylparaben and N-propylparaben, barely separated. By recycling the whole of this peak area though, the second, third, fourth, fifth, sixth, seventh and eighth elutions, we have nicely separated peaks at high purity. Yield should be good, depending on loading, but rate will be low. Although if this is fully automated, once it is set up, it can be left to get on with the job. Another example of peak recycling is this example of the separation of Triton X100, which is a non-ionic surfactant that contains a polyethylene oxide chain with an average chain length of 9.5 units. The chromatograms have been run on a series of GPC columns, so the separation is achieved by molecular size rather than interaction with the stationary phase. Going from left to right, you are seeing the first elution, followed by the second, third, and seventh elutions after recycling. The final example of recycling is another size exclusion example, where we are separating the proteins albumin and myoglobin. The first and second elutions show little separation, but by the time we're getting to the fifth and the 10th elution, separation is good and collected fractions would have high purity. Fraction concentration and desalting. Once we have collected all of our peak fractions, we typically need to concentrate or remove all of the mobile phase. Unfortunately, our fractions tend to be highly diluted, and in many LC purification labs, dry down or removal of mobile phase can be the most time-consuming step in the whole process. In addition, the fractions may contain unwanted salts and buffers depending on what mode of chromatography we use for the purification. By adding a switching valve, trapping column, and second mobile phase line, we have the potential to concentrate the analytes in our fractions on the trapping column before desalting, eluting, and collecting with a strong solvent of minimum volume, thereby greatly reducing the fraction volume we are required to dry down. Summary. LC purification is concerned with physically separating and isolating an amount of one or a number of components in a sample. It is a balance of purity, yield, and rate. Separation has priority to peak shape. Flow rates and sample loading can be scaled to different column dimensions. Your required purity, yield, and rate will influence loading. Use weakest solvent possible for large volume injections. Larger particle sizes can be used in preparative LC. Peak recycling can be used to improve inadequate separations or reduce losses in resolution caused by sample overload. And fraction concentration and desalting can save time and resources downstream. That's all from me. Thank you very much and enjoy the rest of your day.
Excellence in science. Shimadzu.